God morgon och varmt välkomna till Carlos Jorques Morenos disputation med titeln Design and Optimization of In-Cycle Closed Loop Combustion Control with Multiple Injections. Syftet med disputationen är att säkerställa kvaliteten på avhandlingen så att kandidaten kan titulera sig doktor. Disputationen kommer genomföras på engelska och därmed så skiftar vi språk. Warmly welcome to the dissertation of Carlos Jorques Moreno. The purpose of the dissertation is to make sure that the quality of the thesis is such that the candidate can get the title of doctor. The participants of the thesis defense is, apart from Carlos Jorques Moreno, Professor Ming Cheng from University of Windsor in Canada. We have an examination board of Professor Lars Eriksson from Linköping University and Professor Thomas McAlvey from Chalmers University of Technology, and senior lecturer Dr. Thomas Stephan from Loughborough University in UK. And I understand that all the ordinary members of the examination board are online with us. Is that correct?
Yes, I'm here.
So let me say, right. So we don't need to use the substitute members of the committee today. That's great. The supervisors of Carlos Jorques Moreno's work has been Professor Per Tunestål from Lund University, and the co-supervisor has been Professor Ola Stenlås from Scania. My name is Martin Tuner, and I will be the chairman of these procedures. And with that, okay, so we're going to shift over to see the actual procedures, yes. So we are at the opening of the public defense, and the first thing we need to look into is the errata. Are there any changes to the thesis that you would like to mention?
I haven't found any so far.
Okay.
Anybody finds that?
Yeah, we'll probably see that today. So right. Okay. And then we have the presentation by Carlos, and that is about 45 minutes.
We will try.
We will try that, yes. Or you will try it, of course. And then there will be a discussion which is led by the faculty opponent. After that, we will have the questions from the examination committee, followed up with questions from the audience. At that time, we will have the closing of the public defense, so there will be an examination committee meeting to discuss the quality of the thesis and if it's a pass or if it's a fail. And after that, we will have an announcement of the result, and yeah, we will close the sessions after that. So with that, I leave the word to Carlos.
Thank you. So, welcome everybody. The moment has arrived, and thank you all for joining online. I'm really excited to present what I have been working these last 5 years. And I will open this presentation with the question that I usually get when I said that I will start a PhD about internal combustion engines. That is, why internal combustion engines? What would you investigate on that? Shouldn't we instead use electrical vehicles only? So my answer is normally yes, but no. The problem is more complex than that. So I will start with the part that we all must agree. That is, pollution does not only affect our health on a local scale, but the escalating climate crisis is a great threat to our planet's ecosystem and society. So we must therefore reach an economy with zero greenhouse gases emissions. Since the Industrial Revolution, the total CO2 emissions have been increasing exponentially yearly, and so has the average global temperature by almost 1 degree. And this is only increasing and even faster. If we project the future, the previous policies will increase our temperature by 4 degrees at the end of the century. Since the Paris Agreement, more stringent legislation on emissions aims to not increase our emissions, but this is not enough. To meet the targets of the Sustainable Development Scenario of the International Energy Agency, we will need to decrease our CO2 emissions by 60% already by the half of the century. The question is how we can achieve those targets. So if we look at where those CO2 emissions are generated, the largest share is from the energy sector. The transport sector accounts for about 16% of the emissions, being the road freight transportation the largest share. Furthermore, the demand of transportation is only increasing at the rate of roughly 2% yearly. That is why breaking that link between economic growth, transportation, and emissions is a real challenge. We think about last year with the COVID pandemic, we had to stop the economy and it decreased by 7% in Europe. Yet the CO2 gas emissions dropped only by 8%. So how are we supposed to reach the Sustainable Development Scenarios objectives? What we need to achieve is that an increase in transportation does not imply an increase in CO2 emissions. So again, how can the internal combustion engine be part of the solution? Isn't it enough with electric cars? We need to zoom out to understand this. Electric cars are only as clean as the electricity they run on. And still nowadays, 30% of the total CO2 emissions come from electricity generation. Driving an electric car will only change the location of the emissions. And this is a global problem. We will need a transition to the sustainable electricity generation to really make an impact on the reduction of greenhouse gases. This will take time, as 60% of emissions reduction by 2070 will come from technologies not commercially available today. By mid-century, technologies to improve the use of energy and alternative powertrains will help to reduce 34% of emissions in transportation. In the Sustainable Development Scenario, 20% of CO2 savings will be from the widespread of biofuels, which will supply up to 17% of the energy demand by 2060. The great advantage with biofuels is that they can power our current vehicles using the already infrastructure that we have, which will help the transition to a sustainable transport system. This is especially significant for the heavy-duty transportation, as by mid of the century, still 60% of the powertrains will be based on common diesel engines. To ease the transition to sustainable transport solutions, we must ease the use of different energy carriers, ranging from biofuels, e-fuels such as hydrogen or methanol, all the way to electric batteries in order to supply the demanded torque and speed with high reliability, high efficiency, and low emissions. In this presentation, I will focus on biofuels, and the great challenge that they have is that the properties differ significantly from each other. This adds up to the other uncertainties that we have when we operate our engines. Those uncertainties can be classified first by how much we know, how hard it is to know about them, and how difficult it is to adjust to them. So for example, we have the engine configuration, and so far we can deal with those by the adequate calibration of the engine. Then we have also how we run the engine, and we can adjust to those by the adequate operation of the engine. Now we have included the fuel as one of the uncertainties, and together with the engine, external disturbances, and the stochastic random variations, that modifies the optimal set point when we operate the engine. And the way to deal with those is by the combustion control. And this is how it works. What we can do is that inside the combustion chamber, we can include a sensor to monitor the pressure evolution inside the engine. That will provide valuable information that the ECU will take into account in order to process and adjust the injection. In the middle range, the information for the previous cycle can be processed in order to adjust the injection of the next cycle. That is referred to cycle-to-cycle closed-loop combustion control. So as the cycle advances, then we get information for the pressure, we process that information, and we adjust the next cycle injection. There's not an overlap between the feedback and the control action. That has a limitation to deal with the stochastic variations of the combustion. So to deal with those, what we can do is to process that information within the same thermodynamic cycle, which is referred to as in-cycle closed-loop combustion control. And that will be the focus of this presentation and where most of my PhD thesis has been based on. So we'll follow the classical feedback loop in this presentation. We will start looking into the system on itself, looking at the combustion. Then we will look into estimation methods to get information about it. We'll need some prediction based on models. And then we can look into how we design the controller. We'll follow two different approaches to increase the indicated efficiency. The first one is the direct efficiency optimization, and the second one, the indirect efficiency optimization. We'll look into what we need to implement those controllers, and finally a summary. So here we can see the experimental setup. It was a Scania, or it is a Scania D13 engine in line with 6 cylinders. And as you can see in the picture, there are a lot of sensors all around. The ones that we need to highlight is first the crank angle degree position with a resolution of 0.2 crank angle degrees, the in-cylinder pressure sensors, and the intake manifold pressure sensors to do the pressure pegging. We also have torque and speed, and the exhaust emission system. The software was structured in 3 different levels, starting with a PC that communicated with the user and also the exhaust emission system. We also have a lab view written target that interface most of the sensors. And for the in-cycle controller, we use a Vertex 5 FPGA that interface the in-cylinder pressure sensors and was synchronized with the crank angle encoder. So now we can start looking at how does the system behave. So here we have the pressure trace and the fuel injection that is defined by the start of the injection and its duration. The cylinder pressure can give us information about the engine outwork, the load, maximum pressure derivative, and we can also estimate the indicated efficiency. But we want to monitor the progress of the combustion, and that can be achieved by the heat release analysis. We apply the first law of thermodynamics, and then we can get the heat release trace. It gives us important and relevant information about the progress of the combustion from the start of combustion and the crank angle degree at the 10, 50, and 90% total accumulated heat release. Another important parameter is the ignition delay, the time between the start of injection and the start of combustion. When we calibrate the injection, we have to account for the hardware constraints so that we don't break the engine, and also its operation to limit the emission constraints. And here's one example where we have optimized the main injection so that we are under a certain maximum pressure derivative. Since we don't fulfill that, we can delay the main injection until the constraint is fulfilled. But that comes with a penalty on the indicated efficiency of about -1%. Another solution is to inject a previous pilot injection that will fulfill the constraint, but with a much lower penalty on the indicated efficiency. The challenge that we have with the pilot injection is that since it generates a penalty on the indicated efficiency, we want it to be as small as possible. But that makes it harder to regulate, and it has a higher combustion uncertainty and also variability. So that's why we need in-cycle closed-loop combustion control to push the pilot injection as small as possible. So for the combustion characterization, we investigated from the pilot injection, its combustion, the main combustion, and the engine out parameters. We'll only focus in this presentation about the behavior that is relevant for the in-cycle closed-loop combustion control. And we will start with the pilot misfire probability. This is the lack of pilot combustion, and it is most affected by the intake disturbances and the pilot mass. Here we have an example of the misfire probability as a function of the pilot mass. So the more pilot we inject, the lower the risk of having misfire, and the later we inject it, the lower the risk of pilot misfire. This also means that we can compensate the risk of pilot misfire by adjusting its start of injection. The dispersion is uncorrelated, meaning that we cannot get information to know if the current cycle pilot will misfire or not. We need to get all the information from the same cycle. We cannot correlate it to a different cylinder or a previous cycle. About the combustion timing of the pilot, it's mostly regulated by the start of injection, and it doesn't have direct in-cycle controllability, meaning that we cannot get information feedback from the pilot combustion before its injection is finished. About the combustion rate, it's limited for early pilot injections. And this is what we can see here. It is the accumulated heat release as a function of the pilot start of injection. For very early injections, the combustion efficiency is lower than for later injections. It is mostly constant in the heat release shape. And the combustion efficiency is a non-linear function. So if we inject different pilots with equal the injected mass, the accumulated heat release is not proportional to the mass. To study the effect of the pilot combustion to the main injection, we define the pilot-main interaction mode. It's a way to lump together all the different pilot injection parameters so that we can study in an easier way how it affects the main injection. So it's defined by the combustion time of the pilot where the main injection starts. We can define mixing mode, premixed mode, diffusing mode, and completed mode. So the way to understand that is that a later interaction mode is because of a larger pilot mass and larger pilot main separations. So looking at the main combustion timing, it's sensitive to the operating conditions, and it has a high sensitivity to pilot misfire. Once the pilot combustion is stable, it has a small sensitivity to its combustion. And it has higher dispersion at lower loads than single main injection. About the main combustion rate, it's sensitive to the combustion timing and mostly sensitive to pilot misfire. In that case, we will get a highly premixed combustion. This determines also the indicated efficiency. Here we have an example, and you can see that the more pilot we have and the earlier it's injected, the lower the indicated efficiency, except for mixing mode. In that mode, we can get pilots that misfire, so that may increase the indicated efficiency. But it's again the main combustion timing that will determine the final indicated efficiency. So to optimize it, we can adjust the main injection. Now that we know about the system on itself, we can derive estimating methods to monitor the progress of the combustion. So here we follow the whole process of the combustion from the charge compression all the way to the engine op parameters. From the compression, we derive some estimated methods to estimate the specific heat ratio that is used for an accurate pressure prediction. From the pilot injection, we also propose stochastic methods where we exploit the correlation between the pilot misfire and the pilot mass. And in that way, we can estimate very short pilot masses. That is hard to estimate those otherwise. It is based on a Bayesian estimation, and the error was reduced from 1.8 milligrams to plus minus 0.5 milligrams. For the pilot combustion, we need first to detect if we have pilot combustion or not. We need to locate when the combustion starts, and then we can also estimate the pilot mass. And finally, since everything's based on the heat release analysis, we also proposed a method to improve the cylinder volume estimation by compensating for the deformations in the cylinder due to the high pressures. And the error was reduced to 0.4%. This presentation, I will only focus in the pilot combustion and main combustion detection and estimation. So we'll look into the combustion detection. Here we first to detect we have pilot combustion or not. And then we have also to detect if it has started or not. So the detection consists on designing a binary detector. This is to design a function based on some measurements, x, that tells us if we are in one case or the other. Here's one example about how challenging this can be. In the upper plot, we have pilot combustion, since we can see it there from the heat release trace. And in the lower plot, we have pilot misfire that we can identify by the higher premixed rate of the main combustion. The way that we can detect that will be to set some threshold. And in the upper case, we will decide pilot combustion. In the lower one, it's under the threshold, so we decide pilot misfire. But since we don't have any more information, that diagnosis can be wrong. So the question is how we can calibrate that threshold so we obtain a good detection performance. So the supervision variables were the heat release, the pressure rise over the motoring, the accumulated heat release, and then in one of the methods, combining all of them by sensor fusion techniques. We also follow different approaches. The first one was a deterministic design of the detector, and the second one an stochastic. In the first case, we compare our supervision variable to a threshold, and in the second one, we compute the probability of having misfire or combustion, and the higher one, it's the case that we decide. We also investigated different ways to define those functions. The first one was to calibrate the function or the threshold, and the second one, adapting them online. So we investigated a different combination of those, optimizing the threshold over the whole range of operating conditions and adapting that by a cycle-to-cycle feedback. In the case of the stochastic approach, we investigated the direct modeling of the probability, and second, by a stochastic model, computing the posterior probability by Bayes' theorem. And finally, the adaptation of those models and combining them by sensor fusion techniques. To also understand the potential and how good the in-cycle misfire detection can be, we define the in-cycle misfire observability by evaluating and optimize constant threshold at each operating condition. And that will give us information about the signal-to-noise ratio. And here we have those results. This is the maximum that we can get for the different measured variables: heat release, accumulated heat release, and pressure rise, and also their combination. So the constant adaptive threshold, it's not too good. We are far from the maximum that we can reach. Depending on the signal-to-noise ratio of each of the variables, then we get different performances. And in this case, the accumulated heat release is the one with highest robustness. Then the drawback of that is that it takes more time and the heat release is faster. With the stochastic approach, we can increase that, but note that the models were calibrated for diesel fuel, and these results are for HVO, meaning that the stochastic models, since they are not adapted for that fuel, we get worse results than the constant threshold. However, when we can adapt the different models, we can reach detection performances closest to the maximum. And by the stochastic method, then we get better detection performance, but it's more complex, even though they can also achieve sensor fusion techniques. And in that case is where we get the maximum detection performance. However, the adaptive threshold has a much lower complexity, and we can reach very similar performances than that. For the detection of the start of combustion, the binary detector, we follow an stochastic approach where we can model when we expect the pilot to start its combustion. And we can also model how much we trust the heat release signal. And by doing that, we derive a so-called match filter. It's a way to change the detection threshold within the same cycle. In that way, once we get the heat release trace, we can detect the start of combustion very early and in a robust manner. So now that we have decided the pilot has to start its combustion, it's time to estimate its mass. The estimation approach was to describe the combustion as a function of the pilot mass, compare that to the measurements, and then estimate the pilot mass by the reduction of the one step ahead prediction. And here we want to combine as much information as possible. So we start with the pilot injection. The first initial estimation is from the calibration of the injectors. Then we can get also some information from the ignition delay. We can invert the model from the measurement and then estimate the mass and combine that with the previous estimation. And finally, from the pilot combustion, then we get information from the heat release. So we derive a linear dynamic system that was normalized in its states. And then the output matrix was scaled with the pilot mass. And we can minimize the one step ahead prediction by adjusting the pilot mass. So this is how it looks like. Here we have the heat release in the upper plot, and in the lower one, the pilot mass. The red line is the actual injected pilot mass. And then we added artificially an initial error in the estimation. So at the time of the pilot start of combustion, the estimation is not very good, since the ignition delay is not very sensitive to the pilot mass. But once we get the heat release measurements, then the estimation converges to the reference. When we run this over many cycles, then the error at the heat release peak was reduced to ±0.5 milligram from the initial error of ±1 0.5. So it takes around 2 prime angle degrees to get a good estimate of the pilot mass. And this is very important for the in-cycle controllability. So we need to wait that time in order to get the information from the pilot and then adjust the mean injection. This method has some limitations. First is that the model has a linear parameterization, so it limits the range where the pilot mass can be estimated accurately. Also, misfire cannot be pilot when we have misfire cannot be estimated, and it also requires a combustion efficiency model. Another problem that we have for the in-cycle control is that we don't always can get information from the combustion before we can actuate on the injection. And that's why we need model-based prediction. And we'll look into that now. Following the combustion process, we need to estimate or predict the cylinder pressure. We also need to predict the pilot ignition delay and burst mass, main ignition delay, and the engine load. The requirements that we have for this model is that they're not too complex, but still they have high accuracy. And they have to be robust to the calibration. Cannot be that we change the fuel and then we lose a lot of accuracy. That's why that motivates to adapt the models online. We can formulate the models as a dynamic system of the parameters and then already define those models as linear. So the models were these ones, as I said, and we can follow a linear parameterization like this one, where we have 2 parameters, alpha and beta, and an input U and an output Z. Since we need prediction for all 6 cylinders, we can expand the input vector with the input from each of the cylinders and then get the output. And that will be 2 parameters, but that adaptation won't be too accurate, as we will see later. We can instead adapt both parameters individually for each of the cylinders, and that will be 12 parameters in total, which are too many. And we propose an intermediate solution where we adapt one of the parameters for all the cylinders, and the other one is common to all the cylinders, resulting in 7 parameters in total. As we'll see, this has all other advantages as well. Here we have the results in open loop with no adaptation. So the model is the pilot ignition delay and was calibrated for diesel. However, when we run the engine with RME, we can see that we have a wide dispersion of the error. Once we adapt the model, we can reduce that dispersion, but with the common parameters, we get an offset for each of the cylinders as a trade-off of the error of each of them. When we adapt both parameters, or all the parameters, individually for each cylinder, we can increase the accuracy without that error bias. And these are the very similar results that we can get with the reduced multi-cylinder adaptation. It has similar accuracy, and it's also more robust to measurement and input errors. When we use this adaptation scheme for the different cylinders, we observe the same trends of the rest of the models. So now we can get feedback from the combustion, and we can look into how we regulate the combustion. We follow 2 different approaches to design the controller, and the goal is to increase the indicated efficiency. So the first one was the direct efficiency optimization. We adjust injection so that with the information that we have, we can reach the maximum efficiency. And the second approach was a little bit more complex. Here we want to reduce the cyclic dispersion and optimize the set point, knowing how much it is reduced. And I'm going to start with direct efficiency optimization. To understand the potential of this, we also studied the controllability, and we did that by running a simulation model in open loop. So we can see that we have different cases of the pilot, and then we kept constant the main injection to understand how the efficiency is modified due to that. For each of the disturbed pilots, then we took one of the cycles, and then we run it in closed loop without feedback limitations. So we get the main injection, and we maximize the indicated efficiency. Then we also run it in closed loop, but including the limitations of the pilot feedback. So in general, we can increase a little bit the indicated efficiency. In 75% of the cases under 0.2, with a maximum of plus 1% in case of pilot misfire. This is a little bit more significant. Even when we constrain the optimization problem to the feedback window, the penalty on the indicated efficiency wasn't much in very few cases. So with this, we can now design a controller to achieve that maximum indicator efficiency. Since everything has to run in real time, we cannot use such a complex model. And the approach was to describe the thermodynamic cycle as a mixed cycle, somewhere in between an isochoric process and isobaric one. Then we can match the real cycle with an equivalent mixed cycle. And to do that, we define it by it must have the same start of combustion, the same mean heat release rate, and the same load. Here we have an example of the main injection and its equivalent mixed cycle, and the same for pilot and main injection, where we can see that the pilot is fully isochoric process. That equivalent premix ratio can be defined as a linear function of the main start of injection, where both parameters, alpha and beta, are function of the pilot mass. By simulating the mixed cycle, then we can derive an optimal expression for the main start of injection, which is a function of both parameters, alpha and beta. So the next step is to get those two parameters from the feedback. And since the final expression is very complex, we can linearize the controller. So at the nominal operating conditions, we compute the error from the new measurements, and then the linear controller will update the control action and include that to the nominal set point. And by doing that, the experimental results, we saw that we can increase the indicator efficiency by 0.42%. To test that, we run the controller first in open loop without adjusting the main injection, and second in closed loop, adjusting the main injection. And the controller is also able to reduce the load error. This approach has also its own limitations. First, that the linearization limits the range of the pilot masses that can be compensated. It's also fuel sensitive, and pilot misfire cannot be compensated. And the largest drawback here is that we cannot include hardware or operation constraints in the optimization problem, or at least not as easily. And that motivated the second approach, the indirect efficiency optimization. The approach here is again to reduce the stochastic variations. And here we have one example. We can optimize the set point to be under 4.6 bar per cranking degree. Yes. And once we run the engine in open loop, then the disturbances will increase.
Hermano, entrenador de Sandra, Anastasia.
Entrenador de Sandra, ya lo sé, Memo.
So, some problems over there. Yeah. Well, I was saying that when we run the engine, then the worst case scenario will increase the maximum pressure rise rate. So we derive a controller for 4 parallel controllers regulated the pilot start of combustion, burn pilot mass, main start of combustion, and engine load. And the controllers were nothing special, just 4 PA controllers that can be understood as math solvers that update the control output to converge to the reference based on the current measurements. This controller takes the feedback from the predictions until the estimation or measurements are available. And here's one example. We need a way to manage that. Here in the left case, we have a low load, and we can see that we don't have information of the pilot or the main combustion before the main of injection. And in the right case, we can see that we can get information from the pilot and also from the main combustion. So we need a way to coordinate the available feedback in a seamless manner for a smooth transition between predictions and measurements. And also we need to handle if we inject an additional pilot or if we split the main injection. So that motivated a design of the control manager. And what we did is to encapsulate each of the blocks in the feedback loop and coordinate the different cases by a finite state machine. The coordination of those was run by different transitions. They could be triggered by the crank angle degree position, such as the inlet valve closing, also by actuator driven when we command one of the injections and when we finish that, internal event driven when the sensor, for example, detects the start of combustion, and also the coordination between them by external events. When we put everything together, this is how it looks like. Here we have the progress of the combustion, In the upper plot, we have the heat release and the pressure. Middle one, the pilot mass and its on time, and in the lower one, the engine load and its main on time. So the pilot is regulated to reach the start of combustion reference and the barn pilot mass. And the main injection is regulated to reach the main start of combustion and the engine load. So as the cycle progresses, we have different phases. First, we adjust the main injection, the pilot injection, until the start of combustion reference is reached when we command its injection. Then we wait until we can detect the pilot start of combustion. And at that point, we can estimate the pilot mass. Meanwhile, we adjust the main injection until the start of combustion reference is reached. At that point, we command the main injection, and then we can wait until we detect the main start of combustion in case we still have time to adjust the main injection. And the next cycle, the whole process is repeated again. We regulate the pilot combustion. At the point that reaches the start of combustion reference, we command the injection. Then we wait for the pilot start of combustion when the detector says if it has detected or not, estimate its mass, regulate the main injection again, and command the injection. So here we have the load step transient response in the upper plot and the main on time operated in open loop, in cycle to cycle, closed loop, and then the same operating the engine in cycle with the in-cycle predictive controller. Experimental results motivate and support this modular design and that the earlier adjustment results in a shorter transition duration. Also, the finer adjustment reduces the steady state error variance, and the coordination of the different modules avoids pilot misfire during transients and also instability due to closely coupled pilot domain injections. Here we have the same results, but in the upper plot for the regulation of the main start of combustion, and in the lower one, the regulation of the pilot start of combustion for different step responses. At steady state error, the dispersion was reduced between 25 to 75% for all 4 parameters. And that reduction is most significant for the operating conditions with high dispersion. Some limitations of this controller so far is that it cannot compensate for pilot misfire, and the model adaptation for the models that are not too good may result in transients for the in some oscillations for the load. So we need now a way to compensate for pilot misfire. That's the next point. And here we have an example of how pilot misfire can affect the combustion metrics. In the upper plot, we have pilot combustion, and in the lower one, pilot misfire. It delays the main start of combustion, and it advances the center of combustion. We can select either of those 2 parameters, for example, the start of combustion, and adjust the main injection so that it matches the reference. But it will also increase the error on the other parameter. The only way that we can regulate both parameters at the same time is by a second pilot injection. Again, we investigated 2 different control strategies. The first one was a cycle-to-cycle feedback controller with an in-cycle switch that decided which control action we command. In the second approach was a fully predictive in-cycle controller. And in this case, it has also support for the second pilot injection. Here are the open loop results, and both controllers can reduce the error. The in-cycle regulator has also a lower dispersion. But as we can see here, it's not until we inject the second pilot injection that we can also reduce the error in the center of combustion. And as a consequence, it's the only way that we can compensate for the additional maximum pressure rise rate and the additional maximum pressure. So now that we have the controller, we can look into how we can optimize the set point reference for the controllers. That is done by the stochastic set point optimization. We derive an stochastic model, and by a Monte Carlo simulation, we can generate the inputs for the dispersion description, run a deterministic simulation, and then repeat the process a large number of times so that we can aggregate the results and derive the stochastic description of the output. We use different constrained parameters. And we also run the simulation first in open loop to reach the start of combustion set point reference of the main injection, and also the control of the center of combustion. We put constraints on different parameters, and we will look in this presentation at the maximum pressure rise rate. Also, we studied the controllability by not including feedback limitations of the controller. So for the optimal set point results, we have multiple solutions, and depending on which one we choose, that one will have a different robustness. Here we have the set point of the barn pile mass with its associated combustion efficiency. The pilot misfire offsets the nominal point in open loop, and when we compensate for that, we can increase the indicated efficiency by around 0.5% unit. The way to do that is by the regulation of the center of combustion, and the advantage that we have with the in-cycle controller is that we can have one solution for the pilot combustion and another one for pilot misfire. And then the pilot set point will be a trade-off between how risk is to get pilot misfire and then how much we can compensate in such a case. So that when the constraints are relaxed, then the indicated efficiency doesn't benefit from the pilot combustion. And then the optimal solution is a much lower pilot mass with a higher risk of misfire so that we get a faster main combustion. With the in-cycle closed-loop combustion control, we can increase the efficiency by 0.6%, most of the cases, depending on the active constraint, and more significantly at low loads by up to 1.8%. So the next point is, what do we need to implement all of this? So we look into the resources from the FPGA. It was a Vertex 5 with around 17,000 slices composed of 4 flip-flops and 4 lookup tables and 128 RAM blocks. Some considerations for that is, first, we have limited resources, a limited number of slices, and here we have the share of the resources for each of the blocks that we have. Another consideration is the integer representation of the signals that may reduce the accuracy when we run the different math operations. Here we can see that the driver of the injector takes a large share of the FPGA, and that will be a way to release resources, as the driver will be somewhere outside the FPGA. In any case, if we have some limitations, this implementation left a lot of RAM memory blocks left, so some of the operations can be implemented by a lookup table, for example. Another consideration is the propagation delay. We need to run the whole process in real time, meaning that at 40 megahertz, we have around 25 nanoseconds. In this case, we didn't run into problems, but here the heat release part takes a large share of the propagation delay, and all the other operations have to wait until the heat release is reduced. So that will be a good block to optimize, and maybe some other methods instead of the heat release. In general, to be under 80% of the use of the FPGA, we'll need to buy or get one with around 21,000 slices. With this, I would like to get to the summary of this presentation. Following the closed loop feedback loop again, we were able to increase the indicated efficiency by 0.5%. And remember that this is compared to cycle-to-cycle control. So closed-loop combustion control can increase the indicated efficiency even more. In case of pilot misfire, and this requires in-cycle closed-loop combustion control, the indicated efficiency can be increased by 1%. That permits to operate the engine with safer margins and tighter margins as well, independently of the fuel. As we saw, pilot combustion is a significant parameter, and that's why we need the detection of pilot misfire, the estimation of the pilot mass, and even for short pilot masses, we can use the misfire correlation with the pilot mass to increase the calibration accuracy of the injectors. We need predictive methods, and to achieve that, we need the adaptation, since the complexity is limited, and we can obtain a robust adaptation by the reduced multi-cylinder technique that we propose. The controller can reduce the dispersion between 25 to 75%, and it can also compensate for pilot misfire with a modular solution in case we want to expand the controller, add different regulated variables or other control inputs. Finally, we follow direct and indirect efficiency optimization approaches, and both are able to increase the indicated efficiency. And to implement all of that, we need an FPGA with around 20,000 slices. So now back to the first question, internal combustion engines. Yes, but only when run efficiently on sustainable fuels. Thank you very much for listening.
So thank you very much for the presentation. And I suggest we take a 5-minute technical break and resume. What is the time right now? So 6 minutes past 11. Let's continue with the opposition at that time.
Yep.
Yep. So Professor Ming Cheng, are you ready for the opposition?
Yes.
Great. Welcome.
Yes.
And please.
Yes, thank you. I consider it is a very good thesis. The presentation is also very good, the same quality as the thesis itself. But I do have some questions to ask.
Very good.
Yeah. Could you go to your slide 11? Slide 11. You talk about the engine and also your control platform.
Yes.
Yes.
This one. Oh, well.
I can't see. I only see your agenda right now. Now it says thank you.
Yeah, I know.
We are very appreciative here. So.
This one, I think.
Yeah, while you are loading, I can ask is, so you showed the research is relevant to a multi-cylinder engine. So the engine, you have exhaust gas recirculation, turbocharging. So it's a complete engine, 6 cylinders.
Mm-hmm.
Yes. You also mentioned you actually measured the 6-cylinder pressures and also the 6 intake pressures.
Yep.
For each cylinder. That's for your some sort of paging of the cylinder pressure. But here I would like to say is from your majority thesis and the presentation, for instance, your slide 19 to 26, you talk about the pilot detection, estimation, and combustion evaluation, and also the follow-on presentation. It's pretty much more relevant to a single-cylinder engine, a single-cylinder research engine, than a complete multi-cylinder engine. And also you mentioned very little about the exhaust gas recirculation.
Mm-hmm. A little bit. Yep.
Yeah. So how would you consider if a single-cylinder engine research is not sufficient for what you were doing?
It will be sufficient, but the engine that was mounted in the lab was a full engine. In fact, the previous students that worked on this project in the in-cycle closed-loop combustion control, they were working with a single-cylinder engine where they could control the intake conditions and all the process inside the cylinder with higher accuracy. Everything was a little bit better controlled. But the one that I got was a full 6-cylinder engine. And then even though the main idea was to run with one cylinder, then I expanded that to all 6 cylinders, where in this case, they have enough margin between the 6 cylinders to run the same code in all the 6 of them. But of course, that makes it more challenging to really know exactly what's happening, because you have all the different conditions of the EGR and intake air mass affecting individually each of the cylinders. But that's also a better way to quantify how it's the potential of this in a multi-cylinder engine. That
Yes.
with a single cylinder engine, then you can also evaluate the different algorithms. That is not a limitation in this case.
Yes, you have a lot of challenges. It's very good. Yeah. Can you go back to the slide 11 again? Yes.
Yep.
Yes. Yeah. And also, if you like, go to the full screen, go to the large screen.
Let's see if it works.
Yes. Okay.
1 second. I'm trying to.
Yes.
No.
Yes, great. Yes. So this was, if I say is actually, when you run this research platform, you do have at least 2 computer systems. One is your FPGA that is controlled with the interface of the real-time controller and through the human interface as a host of your PC. So actually your engine, for instance, the EGR, the boost pressure, and some other things are actually controlled by another computer. Is that right?
They are controlled by the real-time target. All the controls of the engine, except for the in-cycle supervision, were implemented in the real-time target. And that was
so this is even the turbocharging and exhaust gas recirculation are all controlled by the real-time target. That's a great amount of work, especially for turbocharging. So
it is.
Okay. So this is I have some questions. I think you answered well. That's actually is a tiny amount of things you do wrong. You can damage the turbocharger or damage the engine. So is this engine, your 15 bar IMEP, account for high load or medium load?
It will be medium load. This engine runs up to 27 IMEP bar IMEP.
Great.
That will be more like high load.
Great. Yeah. What is the peak injection pressure of this engine?
I think it's around maximum 2,200 bar.
Okay, great. So you reported something to the middle range, but that's actually pretty good. Yeah.
In the understanding of the in-cycle closed-loop combustion control, the high load can be understood as when you have overlap between the main injection and the main combustion. Because after that, then you have the same kind of dynamic system.
Yes.
That will then modify much your controller.
Yes. In your majority work, you talk very little about nitrogen oxide. So I can assume your analysis is more like all in the high temperature combustion domain. Is that right?
Yep.
Yeah, okay.
It's just common diesel combustion. It's not like PPC or HCCI, low temperature combustion models or concepts.
Yes, but as in your thesis, you also mentioned that probably the urea consumption would be an issue. So one way or the other, the internal combustion got to be some sort of controlled to reduce the nitrogen oxide emission. So I'm just wondering, like your progress, your achievement applied to the high temperature combustion very well, but as we all know, the slope of the high temperature combustion control is quite not steep, quite smooth compared to low temperature combustion. So what would you think your model if applied to low temperature combustion?
Do you refer to the controller strategy or the predictive models?
Both.
Well, first, the models, the structure of the models, they are for common diesel. So they will need an update so that you can also predict the combustion timing and shape in case you run low temperature combustion models. However, the synchronization of the different there, that will be the same. So you need to coordinate when you have information and when you can activate that. Depending on how you run the injection pattern, then you may have different combinations of feedback and controllability of the controller. In case you run with a single injection, then you will have very, very limited controllability on that injection. That will also rely on the evolution of the pressure at the beginning of the intake, and it will be as good as your ignition delay predictive model. If that is accurate enough, then you will have that controllability from a single main injection. If you have more injections, then depends again between the overlap of the combustion and the main injection. So a way you can regulate that will be the coordination between a cycle-to-cycle controller that will take care of the intake conditions that will affect the ignition delay. And you can also regulate the injection timing. In that regard, there were previous studies by Gabriel Tudeson about how you can regulate both the combustion shape and also the combustion timing. Then you can expand that controller, for instance, by supervising the evolution of the pressure to adjust that cycle-to-cycle regulation and understand that as the nominal set point of your control input. Then if you also want to inject other post-injections or injection of, I think they studied in France about injecting oxygen, ozone, that will be another option that you can include in the controller. So you will need a way to understand the system, how it behaves, and the controllability that you will have. That will be the first step to use my research into that.
Yeah, it is a very difficult task. Whenever you're working at the borderline, it's like a cliff. It's very, very sharp. Then please go to your slide 12.
Let's see if we can do this like this.
Yeah, talk about the fuel injection.
Yeah.
Because you have so much talk about the pilot and also the relationship between pilot and main.
Yeah.
Yeah. So I found that in your thesis, you mentioned actually in the presentation also, in many cases you would like to keep the pilot as small as possible.
Mm-hmm.
But it looks like you didn't do rate of injection evaluation. At the end of your thesis, in your future work, you suggested probably the ROI, rate of injection, is an aspect should look into, because the commanded duration of fuel injection,
mm-hmm.
Even if you use the electrical waveform, the current waveform, there's still not much difference with the commanded TTL. So this is when you talk about the detailed pilot mass,
mm-hmm.
so it is better to understand the calibration of fuel injectors. You mentioned the quantity calibration and also the so-called full flow calibration, like you keep the injector open for a long time, like the industry very often for half a minute. Then you measure the size of the injector. But actually, the dynamics is so important,
mm-hmm.
such as the injector, the timing calibration, the opening delay of the injector, the closing delay of the injector,
yes,
the minimal opening duration. You mentioned that this one, this engine, this pump probably is or injector 6 milligrams per shot. But even that actually is not a fixed number. Different pressure, different pump rotation speed, the minimal would be different.
Yeah.
And also the minimal is a minimal opening and also the minimal quality. So this is also the minimal dwell between the two shots. So actually, it would be better if you actually quantified, because if you command the two events of injection, if they are too close to each other, you know that they might just merge to one very fat one.
And that was one of the problems that we experienced with the transient control.
Yes, it's quite dangerous to run the engine that way.
Yeah.
Yeah. How do you comment your some part of like a lack of evaluation of the true rate of injection of fuel?
Regarding the pilot injection, then the challenge here, you could have a perfect injector that you command exactly as small pilot as possible. But as you mentioned, then you have oscillations from the rail pressure pump, from the different injections of the multiple cylinders. That is one part with that. With a single cylinder engine, you wouldn't have as many problems. But again, you have the close couple between the multiple injections. And there's where, again, the in-cycle closed combustion control can play into role, because first, the pilot duration, you can adjust that if you can also merge the sensor of the pressure rail, the common rail. You can monitor the pressure, and if you have enough resolution with the sensor and your ECU, you can also predict how the shock wave in the rail will affect that. And in that way, the in-cycle controller can first adjust the pilot injection. Then, of course, you have the many other considerations depending on how the injector behaves, depending on how is the physical structure. That will be the next one in order to command a short enough pilot injection. So, but you also want to have cheap components, as the price is proportional to the number of injectors that you have. However, this development of the software will be the same. That way you can optimize your system, and you can also get more benefits by regulating the ejection by the software. That means that the injector that you have won't be as accurate. And there's where the highest potential of this can play into role. Then the close couple between injections and the dwell time, that is another parameter that can affect the main injection rate. And to do that, the only way that you can, not the only, but the principal way that you can have to monitor that will be the common rail pressure sensor. There are also some configurations of the engine that you can place a pressure sensor inside the injectors. I think some commercial vehicles have that, but that will increase again the total system cost of ownership. So you can build some of those into that, and also depending on the accuracy of the injectors, that dwell time will be different. The minimum pilot mass, I know that it can get a bit smaller, but you will have, again, the different certainties if that pilot mass will burn or not, even when you inject the same mass. And another thing will be the aging of the injectors and how that affects the dynamics. Then at that point, you don't know exactly how the injector will behave. And then we are again to the starting point.
Yes. The aging is, you are right. Actually, I consider your way to use the commanded fuel injection to do the estimation. It would help the aging. You know that the aging effect, some manufacturers use a knocking sensor to detect the combustion noise, but I think your way might even work actually. But I still like to get into something, into a little bit of detail before I finish my questions. About your pilot misfire. For instance, your slide 40. But there are many other slides you also mentioned pilot misfire.
That's
Yeah.
it. 1 second. We have some
Yeah,
short technical problems.
Yeah, that's okay. So one is the terminology. I'm not sure. I know you published, very well published a lot of papers, pilot and misfire. I think as your own terminology probably is fine, but you know that many manufacturers, they prefer actually on heat release, you see very little pilot heat release. Yes. Then actually, but you do prefer the presence of the pilot, but you don't see it directly of its own flame. But I would say the scenario probably it would be if you discuss the different scenario of a total misfire, such as you don't have a spray, zero spray, or you have the spray quality is so small, it's so poor. Actually, when the injector the pressure is not favorable, your minimal injection quality can be very, very bad. Or actually, everything is normal. Spray quality excellent, but you just injected too early. Not just once, even twice, 3 times. Actually, there's not much apparent chemical reaction, and not much heat release. Like those kind of cases, how would you call it a misfire? They are actually, they help you to generate a better per-mixed mixture. Also including if you use a lot of exhaust gas recirculation, you might also have this case. You could have a region of per-mixed mixture generated by multiple pilot injection even. So this misfire, I think you do have your definition, right? I'd like to see your comments on it.
We're focusing on in-cycle control, and once you optimize your nominal case, then you limit also how fast the combustion is, and that is determined by the premix rate of the main injection, at least in the standard diesel combustion. So what you want is that you keep that, not only the combustion timing, but the combustion shape. So for the in-cycle, the effective pilot is that it will reduce the premix combustion of the main injection. And when you don't have that, it's because it's defined as you have pilot combustion. It has increased the chamber temperature, and then the main ignition delay is a little bit shorter, and you don't have as much premix combustion. I can show that example. It is a little bit here. Exactly. So even if you inject pilot, and even if it will burn, with an optical engine, you could diagnose that pilot combustion in this lower case. I think you can see the pointer. Yes, in that lower case. But the effect at the end is just the same as if you will have the lack of the pilot combustion. There, you can also have more effects the more injections you have. For instance, that the main injection could turn off or finish the combustion of the pilot. But for the in-cycle controller, then you will adjust so that to the new or updated combustion shape. So that is why we define it as the increase in the premix rate of the main injection, because that's the effect that will condition the engine out torque, the engine out noise, maximum pressure, and maximum pressure derivative related to the noise, and also the exhaust emissions, even though we didn't look too much into that. So when we inject the pilot, we just want to keep constant the same heat release shape of the main injection, and that's where the definition comes from. In the legislation, that definition is a little bit different. Then most of the research is about the full misfire, that cycle, which for diesel is not that relevant. In this case, it's about having a change in the shape of the main injection. And there's where the adjustment comes into play within the in-cycle scope of the regulation of the injection.
Great. Yeah. I think your controller use is you are doing very well with the FPGA controller, and your mathematical model actually you designed also very well. It demonstrated pretty good. I think you also constantly mention the resources or the efficiency of programming to use the FPGA. From our side, actually, recently we also expanded to use Intel FPGA. It looks like they have more resources, but the programming is terrifically difficult. For a few months, we don't have much progress to program.
I have experienced that myself.
I think I finished my primary questions, Chair. Thank you.
So thank you very much, Professor Cheng. So now it's time for the grading committee to ask their questions. And I was thinking that we would give the honor to our most distant guest from Sweden, meaning Dr. Stefan from Loughborough University. Do you feel ready to ask your questions?
Hello. Yes, thanks for the welcome. We are far away and yet so close. I think this is great use of technology. And thank you very much for this excellent presentation.
Thank you.
I've got a question about slide 37 because I really liked that slide. I thought it showed better than your thesis what is actually going on in terms of the timeline, and control is always about the timeline, I think. So my key question here is, so how much time do you have between getting your measurement data, being able to make the decision, and being able to take a control action? And can you express it on a timeline, not in crank angles? Because I think, that shows what kind of technological challenge we have here. So at which point can you detect the misfire of the pilot, and when do you have to act on that information?
Let's see. I'm mostly into the crank angle degree world.
Exactly, yeah.
But 0.2 crank angle degrees, we're talking about, if I'm not wrong, it's 400 nanoseconds between every sample of the encoder, meaning that that's the time we have to process everything. And yet we run all the operations in 25 nanoseconds. If we look at the physical part of that, one thing is the separation between the injections. So it's about 1 millisecond, the maximum that we can have, minimum separation. And the delay from the injector driver, that was about, I think, 1 crank angle degree. So again, let's say 1.5 milliseconds. Microseconds, milliseconds, about that time. So we have very, very little time to operate in that. Also, you need to take the decision before or while you have physical controllability on the injection. And well, that was one of the problems that when I was implemented all of that, I experienced that if the decision was too late, then that injection was commanded the next cycle, and it wasn't fun.
And you said your FPGA is running at a 40 megahertz sample time. Is that right?
Yep,
so you can
exactly.
process all your control law at a 40 megahertz sample rate, which is quite a bit faster than you need to be then at the end of the day. So if you say you have half a millisecond, you are still orders of magnitude faster than you have to be in order to make the decision.
Exactly.
Is that right?
Yep.
It is impressive. I was impressed by the speed of your algorithm. That's of course the power of an FPGA. Yeah,
well, it's all the electrical signals propagating through the flip-flops. So
yeah, it's different from a von Neumann architecture, which always takes time.
Yeah, that extra time that you can have from sample to sample, that you can also run multiple injections, multiple operations. I mean, if you have some algorithm that you want to converge, you can include a single loop that to compute or simulate the predictions. In this case, everything was run into a deterministic manner, which is necessary to warranty that you have a combustion, meaning that there's room for more complex algorithms, at least with this FPGA. Or on the other hand, you can have a cheaper FPGA without that many computational resources. And that's a way to evaluate how far you are from the optimal and what you need.
Yeah, very good. Okay, second question. You talked about detection of the misfire of the pilot. Did you also try to predict the misfire of the pilot injection based on information that you have available before the pilot injection?
I tried first experimentally, and that's what I named with the uncorrelation of the pilot misfire. So in that case, we studied what is the correlation. If I get pilot misfire in one cylinder, will I get that pilot misfire in the next cylinder in the firing order or the next cycle? And with the ANOVA analysis, then we saw that there's no correlation, meaning that I can only predict pilot misfire from the information that I have with the current cycle, which is a little bit of limitation, but then you can monitor the intake pressure and temperature and the evolution. And then based on that, you can adjust a little bit. So even though you will be maybe a little bit offset of the burn pilot mass reference, then you can adjust, so at least you're over the limit. In that sense, we haven't built any model stating that at which trade-off or threshold of the pilot mass with the operating condition you will have pilot misfire, because that will be a way to push to the limit the reduction of the pilot mass. That'll be very interesting, actually. But nothing done yet. Yeah.
Okay, final question. Do you have a needle lift sensor in your injector? Because we have one and we found it very useful to see what's actually going on, because there is the main time delay, a big time delay is the needle lifter.
Yeah, no, we don't have any sensor there.
That's a shame, you know. But
yeah, it'll be good to have that at least in the lab setup to know what is that delay, and that will give very valuable information about the controllability from the command of the injection to the actual injection of the fuel. But no, it was standard injectors.
Okay, thank you very much for your answers.
Yeah,
that was excellent.
Thomas.
Thank you very much for that. And with the decreasing physical distance, we are now in Linköping. So Professor Lars Eriksson, are you ready to ask your questions?
Yes.
Please.
So, thank you very much for a very nice presentation of your thesis. I really enjoyed reading it, and I think you made quite a good selection on focusing on it. Of course, I would have heard much more, but from the time given, I think this was a very good selection and wise choice. So, congratulations to broadcasting your method and the approach. I will just ask a few questions on the modeling that you're using to predict what is going on here. I see you're laughing because the grading committee you select controls what questions you get.
Yeah.
And since I'm a modeler,
your expertise in the modeling of combustion.
Yeah. So after all these years, what parameters in your model is the most important one to get right? I see you had a very interesting extension with the changing cylinder volume due to heat, which I find quite interesting. But what is most important to get right, to get this going?
It will be the ignition delay, first of the pilot, and for the main it will be the delay between the start of the injection and the center of combustion. And that second one is a bit challenging because it's dependent on the shape of the heat release. And it was mentioned looking into which parameter will be relevant to regulate or define the combustion timing. So at least from this optimization setup that they run, it was the center of combustion. The results weren't that good when we related the start of combustion. That will be the next step. And again, for multiple injections, in this case, we don't have overlap. And if we had overlap, that will be something to look into as a very important model in order to predict how the combustion will shape the heat release trace and engine out work and all the rest of the parameters. So that's the fundamental ones.
Yeah. Coming to the modeling, or sticking there, you did not include crevice modeling or blow-by.
No. These models have to run in cycle, and they cannot be that complex. Even I tried to implement linear models, and even for the load, that generated some oscillations during transients because the range is not that good. For the heat release analysis, even we saw that that was the largest time delay of the operations, including even heat transfer or crevices. That will be quite a big challenge.
Okay,
For
yeah.
offline analysis, then you can definitely include that. Why not?
Yeah. Excellent. One more thing on the modeling. And the stepping that you're doing in your predictive. Can you explain a little bit what goes on in the prediction step of your controller when you're predicting one sample ahead?
Yep.
Right. And what is going on in the FPGA then?
Okay, we can start with the pilot start of combustion prediction, for example, and I can use this slide already. So here at the beginning, we have the start of the pilot injection and the model. Here we have actually two models running at the same time. First is the model of the compression ratio, the heat release, heat capacity ratio, sorry. So the gamma, that is adapted online. And then we use an equivalent gamma, so that we don't need to recursively iterate through the pressure evolution. So we just have, we set at -40, the set point reference for the pressure and the volume. And then with the same kappa, because it's the equivalent one, then we predict all the way to the pilot start of combustion. We need to do that because that's the parameter that we regulate. And then we try to place that at the reference, that is this stroke line. That will be the first step. So that only takes one operation with the intermediate calculations, but that's just one step prediction, even though it's many different crank angle degree samples. For the Barn pilot mass, then it's the same. It has a model depending on the injection parameters, and you can actually take that. So we can look at the prediction models. Let's see. If it wants to open, very good. I think it should be somewhere here. Yeah, this is the one. So this is the Barn pilot mass model. It's proportional to the injection on time, the rail pressure, and the ignition delay. It's a fusion between the combustion efficiency model and the injected pilot mass. Here again is just one simple operation, and then with the updated values of the rail pressure and the ignition delay that we're trying to control, then we can adjust that. So for the feedback loop, it's just one operation, then depending on the error, it adjusts that. The next step, we can get back to this one. Running in parallel, then we have the prediction from the main injection. In this case, we need the pressure at the start of the main injection, because that's the input to the model. And that is why here we simulate the pilot combustion as an isochoric process. You just rise the pressure, and then with the same simple pressure prediction model with equivalent kappa, then we compute the pressure at the start of the main injection. At that point, it takes three operations. We need first the first part, the combustion, and then the second part. It's fine because they can run in parallel. The only thing that you may consider is the implementation. How many blocks do you want to use in parallel? That will need more resources. That's a different story. Then now that we have the pressure at the start of the main injection, then we predict the main ignition delay. Again, it's a simple model following the Arrhenius expression, and then including a little, some of the parameters like the pilot injection, and I can bring that up. it is this model here. So it has the pilot misfire, that's a delta variable, because it's the one that has the largest influence. Here we have the blue line, that's pilot misfire, if not pilot combustion. So that's the most important one. Otherwise, we have the pressure at the start of injection and the rail pressure and so on. And then from that, a simple linear model also predicts the engine load. So both predictions correlated to the parameters that we have the control of the pilot and the main. Then they're predicted at the same time, running in parallel. And as the cycle progresses, then we update all the calculations in parallel. That's one of the greatest advantages of using the FPGA. That you don't have a sequential processor, rather than you can compute everything in parallel in real time. But again, since we have a sequence in the progress, then you need to synchronize those parallel operations. And that was handled by the controller manager. And when we investigated that the no coordination of the operations was one of the problems, but then it was able to overcome that. And that's a little bit how it works, the whole sequence of calculations.
Yeah, thank you very much. I could spend the whole day just discussing the research with you, but for the sake of time, I leave my other questions for when we can get more social.
Yeah, definitely.
Yeah.
Thank you very much, Lars.
So I imagine we will meet in the area of vehicles and sustainability.
Totally, yeah.
Yeah, so thank you very much once again, and congratulations to a very nice presentation of your work. So
thank you,
with
Lars.
that, I stop my questioning.
So thank you very much for those questions. And just like you mentioned, there's always an opportunity to continue the discussion afterwards.
Always.
The dissertation. There are many things to discuss in the future for sure. So we're moving closer to Lund, and we will stop by at Chalmers University of Technology in Gothenburg. And Professor Thomas McCalvey, are you ready to ask your questions?
Yes, thank you.
Please go ahead.
Yes, first I would like to make the comment on that everyone else has made. You made a very good presentation of this extensive work, and it's not so easy to pick out the key parts of so many papers and so much experimental work that you have done. But I think you did a very good job here. And also, as pointed out before, this slide 37 here, where you really showed what's going on and how it's timed, was very informative. I must say, very well done. I'm going to be the estimator person here, or the signal processing person a little bit here, and maybe statistics also. So I have a few sort of very basic comments and questions here to you. So a lot of your, or almost all your experimental work are, you give bounds that you, in the text, call 95% confidence intervals.
Yes.
So, so what is a confidence interval?
Confidence interval is the range that you expect 95% of your measurement data to be within. That assuming, then you can calculate it in different ways depending on your assumptions of the dispersion of your data. Usually it's 3 standard deviations depending on the range, and
2.
3 sigma. Yeah, I think it's 2 sigma. That assuming a normal distribution, which usually in this case
you never mention this assumption anywhere in your thesis.
That assumption is taken at least for the pilot mass estimation based on the misfire probability. In that case, it's an asymmetric distribution.
Hold on. I mean, you're doing this on measurement data, right?
Yep.
So are the measurements from a normal process?
Yeah. In the modeling part list, then the dispersion of the parameters and the engine out, then we run a hypothesis test to check that the dispersion was normally distributed. So even in the text, it's not stated clear, but then in one of the papers at the end in the appendix, then you can find that it's actually tested with the hypothesis test, that is normally distributed. In general, since also you have a lot of measurements, a lot of cycles, a lot of cylinders, then that will converge to a normally distributed variable. And that's the assumption at the beginning, at least.
Yeah. No, it's, I mean, a different way. I mean, this is very standard to call this confidence interval, but it has this hidden assumption of normality. Otherwise, you cannot connect the confidence with the estimated standard deviation from the data.
You can calculate it with some other methods, but it will be a different interpretation, a way of calculating it.
Indeed, but this is very standard. But this is a thesis, so now you get to pick a little bit on different things. On the same topic, if we go to your paper 3, where you talk about optimal combination of estimations.
Yes, that's related to this slide. Yeah.
Well, yeah, but I was more interested in the equations in paper 3. There is equation 5, 6, 7, and 8.
That's it. Let me pull the. Do you know the page in the thesis?
I don't think I see the page.
It's in the paper. Yeah.
I have the essay page, which is 1169.
Yeah.
but that's in that volume.
That's in count. This is the.
But if you go paper 3, it's just in the beginning of paper 3. If you take it from there, yeah, exactly.
There we go.
Yeah.
Yeah, that one. Mm-hmm.
Yeah, exactly. So here you very, very well, you clearly state that you are assuming normal distribution.
Mm-hmm.
And then you make, in equation 5, you make an optimal combination of different estimations of the same quantity by weighting them with the inverse of the variance.
Exactly.
Yeah. So this way of optimally or combining different estimates, are they only valid for normal distribution?
In this case, yes. Otherwise, you will need to compute the posterior probability by those the individual distributions, and then you can optimize the total dispersion. Okay, but
the optimality here, the selection, I mean, since you weight together three values, you can actually select any 3 values that you optimize with, it still will be an unbiased estimator, right?
Yep.
So what is this particular way of optimizing? What is or combining them? What is it optimizing?
It's optimizing the final dispersion of the estimate, depending on the accuracy that you relate to the dispersion.
Covariance, you mean the covariance error?
Yeah.
The error, yeah. Exactly. But the covariance only deals with second order properties of the stochastic variable. So this way of combining then is optimal for any distribution, as long as the first and the second order moments exist. So it's not restricted to normal distribution, which is good for you because you're working with
and the assumptions are even better in case they don't hold.
So you don't need the normal distribution assumption here.
Okay.
Equation 6, I looked at it several times and I wondered, this was an interesting equation. I haven't seen that before. So if we take the very simple case and let's assume all the variances are equal to 1. So that means we have 3 measurements, all with the same variance. We can say them 1.
Right.
And we combine them. Then we divide. Then it would be, we would divide by 3. We add them together and divide by 3.
Right, yeah.
What is the resulting variance according to equation 6 there?
It will be 1/3 of the injected variance.
It will be 2/3, right?
2/3, yeah, exactly.
1 + 1 divided by 3
Mhm.
multiplied by 1.
Yeah, I'm aware of this step. That can't remember exactly how I computed that, but the idea was to compute the variance of the combination in the equation 5.
Yes, of course. Yeah.
So
Indeed.
I'm aware that this is not right, this step. Actually, that's why in the thesis, that step was a little bit different with the final estimation instead of that one. In this case, the idea was to do it recursively, its crank angle theory sample. So that's why that needed to be updated each step.
Yeah. I mean, you do that in equation 7, and now you have two measurements. Sort of, you have your previous estimate, and then you have the new estimate, and then you optimally combine them again with the same idea.
Exactly. But
So
then
equation 7 is right, but equation 8 is not right.
It's the same issue as the one before. Yeah.
So if you do this way of tracking the variance, it will not work optimally. Okay. Right. So you use heavily the pressure sensor, and in order to find all the properties that you need in order to do this in cycle control. Of course, everyone who makes engines, they would probably not be too happy if they have to install 6 pressure sensors in each cylinder, etc.
Not at all.
So no, not at all. Particularly not the company you work on, maybe. So what are the alternatives if you want to go with this in cycle control? But can you ease in some way? Can you expand on that? Can you ease in some way the need for sensing?
Yeah.
Still obtain maybe not all the results that you have, but at least something that is still beneficial in the end.
Yep, of course. One way that it's already implemented, I think, in industry will be to use only one in-cylinder pressure sensor. Then you will be saving 5 in this case. And then you can have some estimation methods from the, perhaps even the torsion of the crank angle mechanism, the crank mechanism, then you can more or less estimate also the evolution of the cylinder pressures of the others. That'll be one way. The most extended approach to deal with this is by NOx sensors that you can also optimize where they're placed to get information about the different oscillations, and from that get some hopefully close to the pressure signal. But that is quite challenging because it's not that robust of a measurement. So another approach that you can do is to combine those and then combine many information from different sensors so that you can estimate that final in-cylinder pressure signal. If the timing of all your computation is fast enough, then you can also implement the in-cycle controller there. You can combine that by the acceleration of the crank mechanism, and that will also give you information about the pressure evolution. So perhaps combining the information from a NOx sensor placed in a good position with the acceleration of the crank encoder, then you can get somehow some good estimate. You can also use the spark plug as a way to measure or estimate the ion current inside the cylinder. That is mostly for spark ignition engines, but why not? You can maybe use a cheaper sensor to monitor even for diesel engines. And those are the most widespread techniques to get that estimate.
At least the academic.
Yeah, exactly.
Academically explored to some degree. Yeah.
Yeah.
Yeah. Okay, so a little bit on your detection techniques. And detection is of course a binary decision problem where you have some measured variables and then you try to decide between 2 different hypotheses. And of course, in that process, this decision threshold is of course key, because that's the one that separates out when to declare a misfire or not.
Mhm.
Your application is quite interesting in the sense that you have at least to some degree direct feedback after a while, whether your detection was right or wrong, which is quite interesting. And I like the idea of doing this feedback, which provides a lot of robustness in that sense.
Yeah.
You then suggest, particularly on page 97, 638, you have an update rule in your
In
thesis.
the 97 in the thesis.
Yeah.
Yep. The update. Yes.
Yeah. So it's sort of a proportional controller, although the error variable is 0 or 1 or
yes,
-1. So it only takes 3 values, the delta minus delta hat, I assume. This is how you do it, right?
Yeah, those deltas is the misfire diagnosis, in-cycle diagnosis, and the cycle-to-cycle diagnosis, once you have all the information.
Yeah, exactly.
That will mean that if it's wrong, then you will have a correction. If not, you don't touch anything. Right.
And you suggest, or you have implemented, I assume, this gain, this feedback gain, such that the gain decreases the further away you are, which seems, at least to me, counterintuitive, particularly because if you're very close, then you will make maximal updates.
Yep.
Wouldn't that lead to oscillations in the decision variables?
The main idea here is that when the diagnosis is wrong, but very far from the threshold, that's usually an outlier. So you don't trust those diagnoses that much. And that's what is counterintuitive, the way that the gain is updated. But when you're too close and you don't want to touch it too much either, but then depends on, let's see, the distance.
If you make
it will be
just
oscillating.
a slight small miss here, you would
you
take
need
the
to
maximum
also
step.
It will oscillate a little bit, but those around the edge of the detection threshold, then that gain k shouldn't be too much. So then you do it recursively, but again, you're within the threshold between a signal of misfire or noise. And I can show you the case of that, how it looks like. I think it is here. So this is how it looks like on a cycle-to-cycle level. Those are those oscillations that you're actually mentioning. But take this case. I don't think you can see. This case, for example, is one example of the long threshold. So you're within the kind of noise threshold if either of the algorithms fail. But when you're here, then you want to adjust it a little bit faster when you're within that threshold. And that's why we propose to do it inversely. It's right that you need to be careful, because that may get into some oscillations, as it happened here. But again, those oscillations are correlated to the signal-to-noise ratio and how it behaves in the system, which is very sensitive and not as correlated to the signal to the prediction of the misfire. But you're right in the sense that it may generate some oscillations. Then you can play a little bit around with this let's see, the small quantity that you add in the denominator, so it's not as sensitive to the oscillations. And if that becomes a problem, of course, you can update the correction algorithm in that cycle-to-cycle loop.
Okay, excellent. I will not go too deep here, but I have 2 questions. So if you now get into a helicopter and then you lift yourself a couple of 100 meters above your thesis and then look and see what results in the thesis do you think now, sort of in retrospect, after everything is done, is most important from an academic point of view in the sort of academic area of combustion?
My impression is that the stochastic method should be more widespread in general for the combustion description and also for the control methods. Here, when we talk about in-cycle closed-loop combustion control, it all boils down to reduce the dispersion of that, and it's where the greatest advantage could be. If you ask me now if I will run these first initial experiments in the same way, I will look much more into the stochastic description. Even though it's a little bit there are many more questions that you can look into the correlation, cross-correlation of the different variables and how that affects the final dispersion. That will be the main outcome from this. The rest is mostly model predictive models, predictive control, which is nothing new nowadays. But even though they are necessary for the in-cycle control.
And if we rephrase the question slightly and ask what are the most important results from an industrial point of view?
Will be again how you can optimize the calibration of your setup by the stochastic description. There's a lot of effort is put into how you tune all the parameters, but if you can model the dispersion of that, then you have a systematic manner for the calibration. And that will save a lot of time, even though you need a model. But those models, you already have them. By including the dispersion, then the calibration, you know how robust it is, how sensitive it is, and where you should place it, and how much you can trust it, in case you need to update your model or not.
Okay, thank you very much.
Thank you, Thomas.
So thank you very much for the questioning. And now it's time for the audience to ask questions. And since we are some people physically present and a number of people joining through internet, I suggest that you state your name and affiliation with your question. And I'm not sure I can see online if they are raising the hands. Is that possible, Robert?
It is possible if they are raising.
Okay, so you can, if you're participating online, you can raise your hand before you're asking the question there. Possibly it can also be sent by chat, but make sure that we can see your name. So who wants to start first?
I think Lars Eriksson may want to ask some more general question. Can check that.
Yeah, if it's time, I don't want to take too much of the time and go over lunch. And now, since I mentioned the magic word lunch, everyone is sitting there tapping, wondering. But for the PhD research, it's supposed to be a very joyful time, and you have done a lot of work during this time. And I want that this is also exposed to your friends and family. So yeah. I will ask two questions related to your research. And one is, what of the works that you have been doing have been the most fun to do? Do you remember some points where you had felt like you had really fun doing it? And not necessarily the same results, but which result are you most proud of? So
the most fun ones was mostly when I talked to my supervisor Ulla, and I said I came up with some new idea, even though it was out of the planning of the project. And then he supported me. That was always fun to try new things. Then I tried, and it was very frustrated, but it was good to try. some of them worked, and I'm mostly proud about, again, like the stochastic approach. I'm very proud of that. And mostly to get a controller that worked and was able to increase the efficiency. Also, at the end, put everything, all the pieces together. That felt very good. At the beginning, I had no idea where I was going, and now everything makes sense. That feels very good, and I'm very proud of that.
That's great, and it's also great to see that it was fun coming up with new ideas, and
always, yeah.
Seeing that they are attached to the neighboring colleagues, etc. So yeah, great. So I hope you feel still that you have had a lot of fun years, and hopefully many more coming fun years as a researcher in operation. So with that, my final questions.
Tack så mycket, Lars. Och Carlotta.
Thank you. Do we have any more questions?
Yeah, Carlotta has a
Carlotta
question.
raised her hand. So please, Carlotta.
Thank you. I'm super impressed by the whole presentation, and it's been super interesting, even though I've had the chance to follow you somewhat during the majority of those years, at least. But I was thinking, and maybe it's a little bit outside your work, but looking at the like both misfire and the variance in the combustion traces, but looking at them over time. Like I see now you've been looking at them like from cycle to cycle, but looking over lifetime, like a new engine versus an old engine. Because you mentioned that the technology is probably not financially suitable today. Do you see that there are some can you see any like traces on the same individual over time that it would be of interest to
that will be
perhaps use these extra equipment like earlier in an engine lifetime as an adaptation and then remove it? Or is this something you've considered?
So that when we describe the different cylinder to cylinder dispersion, for example, and the different injector to injector, then that dispersion will increase over time as the components won't age the same. And that's why we need the adaptation, and that's our techniques that they're already implemented in vehicles. There will be a lot of benefits into implementing this. So the larger the dispersion that you have in the combustion, then the larger the benefit. Because those safety margins that we need to include when we optimize the set point, those are quite large if you also include the final dispersion due to the aging. It'd be really interesting to get an old engine, place it with the sensors that we need, and then run these algorithms and compare that to open loop. And we probably see that the increase in the efficiency, it will be closer to 1%. And also, again, how that looks when you're running with different biofuels. We haven't looked into the degradation of the biofuels. We just assume that it will be the same, but then running in open loop and how the engine behaves, that will be quite a challenge. And we're approaching that stage now at the developing phase of our engines where the biofuels play a more important role. And we already see the challenges that we're facing when we calibrate the engine. So far, we only calibrate those for diesel. And you don't know, well, we can know how by running a different fuel will decrease the efficiency or even increase it.
So it's likely to say that this more in-depth estimation with sensors would probably make more sense for like an old tractor fleet rather than the new one.
You can monitor that by different scales. We're going to start with the adaptation over time. But they're part of that it's a little bit harder to adapt. And that's why the stochastic variations play a bigger role. Then when the engine is older, those variations, it's not enough by adapting the controllers that we already have. You need a finer tuning to decrease those. Otherwise, then your safety margin will also need to be adapted, and then the final energy of the engine, efficiency of the engine will be lower regardless. And we'd like to have as old as possible engines out there in our trucks.
Oh yeah, but would it make sense to have it like, if you imagine having the truck or the engine coming into a workshop, and where you would only for a certain amount of time use this equipment?
Yeah, definitely.
And like run the adaptation, I don't know, for an hour or so, and then
that
take
would be
it off.
actually a good intermediate solution on how to apply all of this. Then you just put it in the workshop, you run your automatic adaptation, and then it updates the calibration of the engine, and it will be a bit better than not doing that.
Yeah, because I was thinking then you'd only need, well, maybe it's impossible to mount it and dismount it in a suitable way, but yeah, super interesting.
Thanks, Carlotta.
Thank you, and congratulations to finishing this work.
So thank you, Carlotta. I didn't catch your name and affiliation.
Sorry, Carlotta Vale is my name, and so I'm a co-worker at Scania.
Excellent, thanks.
Yeah.
Good questions. So how is it? Do we have any more questions online? I cannot see anyone.
Not in the chat either.
You cannot find anything, Robert?
No.
On YouTube either.
Anyone else in the room? Per. Please go ahead.
Yeah.
So it's Per Tunestål from Lund University.
Yeah, so I'm curious to know, will you be able to continue working on similar things or developments of this after your PhD thesis now?
Not exactly the same, but definitely supporting my colleagues that will work with the combustion supervision. The next step will be with batteries, actually. Yeah, some hybrid systems that then we will take one more step into how we can fuse these two systems, and knowing how the combustion works, then we will know how we need to develop the next step for a sustainable transport system, which is at the end the final goal. Then I guess if we move to some more alternative fuels, then that will be another kick to the development pace of that. So definitely I'm going to be around to get questions. Yeah.
Thanks.
I think that sounds really interesting. So looking forward to that. Yeah. Right. I don't see any more questions. So with that, I propose that we end the open part of the dissertation. Those of you who are online, you can stay where you are online. The broadcasting will be paused for the closed part of the meeting. So I will ask the faculty opponent, did you get the link to the closed meeting?
Yes, the closed meeting would be on Teams or still on the Zoom?
Teams.
So Teams. It's on Teams, yes, and yes, there's a separate link for that, yes.
Yes, I checked yesterday. Yeah.
Oh, excellent. So we're going to move into that very soon. I will also ask the grading committee, is it someone who didn't get the meeting link for the closed meeting? So it's silence.
I have to say I'm not 100% sure. I had a meeting request, but it was also cancelled. So
no, but it's a new one that you got I think yesterday.
Okay, I will check. If not, I'll give you a call.
You got our telephone number, so should it be any problems?
I've got it. No problem. Thank you.
Excellent, excellent. All right, then we close the open part. We ask the audience to leave this room, and for the grading committee and the faculty opponent, looking forward to meet you very soon in the closed meeting.
Okay, do you hear me?
We do.
Yep, very good. Okay, so the committee has had the closed deliberations now, and the chairman of the committee, Professor Thomas McKelvey, will now announce the results.
Thank you, Matt. Thank you so much, Per Tunestål. The committee has had its meeting and performed its deliberation, and we also have had some checks with the supervisors and the opponent about additional input. And after this, unanimously, the committee has decided that we have passed this thesis. So, and hereby I would like to congratulate you, Carlos, for a well-done thesis and presentation today, including the answering sections as well. So once again, congratulations.
Thank you very much.
Okay, and then there is a present. I think this is the present from the department because it's the only one I received. So there will be a present from the colleagues, combustion engines as well.
Okay. Thank you very much. Let's see what it is. Yep. I need to prove.
May I suggest that everyone turns on their camera, that we could give a nice round of applause for everyone that joined this thesis defense.
Wow.
It's nice.
Yeah.
Very
We need
nice.
to find a good place to put it there.
Yeah.
There we go.
Okay, so Nika, I think, has the present from the colleagues.
Oh. Hi, everybody.
Thank you, Carlos, once more. It was, of course, expected that you will have an excellent presentation and excellent defense. I would like to say a couple of words also. It's clear for everyone who have a look on your thesis or you know your scientific work that you are a really smart, intelligent person. But as a person who have worked with you, I know that you are also very humble, very kind, very caring person. To cover this, we actually donate a small money on your behalf to child education as a gift for you.
That's a really good gift. Thank you.
I'm happy you like it. And it's another gift from your colleague with the name as
Okay.
usual.
Thank
And
you very much.
congratulations again.
Thank you.
Thank you.
Okay, I won't make a long speech here, but Carlos, as your supervisor, and I think I speak for Ola as well when I say that it's been an immense pleasure to be your supervisor for these, how many years has it been?
5 and a little bit more.
5 and a little bit more, yeah. You've been working as well during this time, so not just doing your research.
Yeah.
Yeah. So thanks a lot for this time, and the best of luck, even if you're going to be working with batteries.
Thank you.
Yeah. So I don't know, Ulla, do you want to say a few things also?
A few words as well.
Yep.
So we have a tradition at Scania to hand over a truck.
Right.
But
Come over here so they can see you.
Yeah. We have a tradition at Scania to hand over a truck, but due to the COVID situation, there's been some trouble in having it signed.
Yeah.
So it's still in the round robin process.
Nice.
But you will get this picture of the truck and it can be picked up
Very
later
good.
at Scania.
Amazing.
Then, as we all knew, most of your research has been focused on biofuel and how to make things more environmental friendly,
Yeah.
and also how to get your control system to adopt to new fuels.
Mhm.
And you never ever hand over a truck without fuel.
Mhm.
And I know that you are a great fan of Spanish inspired drinks.
Mhm.
But I think we need to get your control system slightly out of the ordinary area, and thereby I hand over this Scotch medicine,
Yeah.
which is finished in Oloroso barrels. So I think your control system will have at least a chance of coping with
Definitely.
it.
So adaptation to that.
Yeah. So best of luck, Dr. Carlos Jorques Morel.
Thank you very much. I'd like to thank you, both of you and everybody, for listening to the presentation. It has been a great pleasure working with you. Very easy, not at the beginning, perhaps. I always define when people ask me if I use the do the backup and how that helped me a lot to go through all of this. And I really appreciate the freedom that I have had to explore different areas and really get the most of it. It's been a really, really good time working with you. And I hope it will continue. Yeah,
Absolutely.
thank you very much.
The pleasure is all ours. So thank you, Carlos.
I think that's it. I guess we end the defense. It was on a successful note,
Yeah,
which is of course very positive for all of us.
always.
It's
Yeah.
a great work and fantastic day, I would say.
Yeah,
Okay, everyone, take care. Bye-bye.
thank you, everybody.
Bye.
Hopefully see you all soon.
Bye-bye.
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 Thank you.